This is section 4.3 of MA 104. In this first problem, we're asked to write p of x as a product of linear factors. As it is right now, p of x is a third-degree polynomial because of the 3 on the exponent, which means that I have to find 3 linear factors of p of x. I'm told that -1 is a 0. Since -1 is a 0, I know that x minus -1 or x plus 1 is a factor. So I can immediately say that one of my linear factors of p of x is going to be x plus 1. To find the remaining factors of p of x, I can use the idea that since x plus 1 is a factor, or since -1 is a 0, if I set up a synthetic division table, then I can use synthetic division to find the other factor that I can multiply x plus 1 by to get p of x. The coefficients of p of x are 1 for 1x to the third, 9, 24, and 16. So these are the numbers that I'll write on top of my synthetic division box. 1x to the third, 9x to the second, 24x, and 16. And then I'll put the -1 outside. To go through my synthetic division process, I'll bring the 1 straight down, and then I'll take -1 times 1 is -1. That goes up underneath the 9. 9 plus -1 is 8. I'll repeat that process. -1 times 8 is -8. 24 plus -8 is 16. Repeat the process again. -1 times 16 is -16. 16 plus -16 is 0, which we expected since we knew that -1 was a 0. Since I took the polynomial p of x and divided it by x minus a -1, these numbers represent the coefficient of my quotient. They also represent the coefficient of the other factor of p of x. So p of x is x plus 1 times this polynomial. So times x to the second plus 8x plus 16. So I've rewritten p of x as a product of factors, but they're not both linear. I have a linear factor, I know that because it's just an x, but then I also have a quadratic factor that's x to the second. To factor this quadratic even further, I could use the quadratic formula, or I could see that this one does factor pretty easily into x plus 4 times x plus 4. So my 3 factors of p of x are going to be x plus 1, x plus 4, and x plus 4. If I rewrite p of x as a product of linear factors then, p of x is equal to x plus 1 times x plus 4 times x plus 4. In this problem, we're asked to find all roots exactly, which is another way to say that we want to find all the solutions to this equation. It's a third-degree polynomial because of the 3 as the highest exponent, which means we're looking for 3 roots. In order to start, we can start by finding all of our possible rational roots, or possible rational zeros. And to do that, we first need factors of the constant term, the term that doesn't have any variable with it. So I have to find, in this case, factors of 1, which is the easiest number to find factors because factors of 1 just include positive or -1. After I find the factors of that constant, I need to find factors of the leading coefficient, or factors of the number with that very first term. So in this case, that would mean factors of 2, which are just plus or minus 1 and plus or minus 2. My possible rational zeros then, or in this case, my possible rational roots, is just every combination of number that has the factors of 1 in the numerator and the factors of 2 in the denominator. So that would include plus or minus 1 over 1, which is just positive or -1, and then plus or minus 1 over 2, which is just plus or minus 1/2. again, these are just the possible rational roots. Not all of these numbers are going to be roots, and there could be others beyond this that are not rational. To find out which ones work, though, I can use synthetic division. And what I'll do is I'll test each number, and I will test it by taking the equation, or taking the polynomial that I am taking the equation for, and placing those coefficients at the top of my synthetic division table. Notice how I have an x to the third, I have an x to the second, I do not have an x to the first power, so I have to make sure to include a 0 there, and then finally a positive 1. So this gives me 2, -5, 0, and 1. That represents the 2x to the third minus 5x squared plus 0x plus 1. And then I need to just start testing my numbers. I'll start by testing positive 1. I would bring down the 2. 1 times 2 is 2, plus -5 is -3. 1 times -3 is -3, plus 0 is -3. 1 times -3 is -3, plus 1 is -2. I'm looking for zeros of that equation, or roots of that equation, which means I'm looking for numbers that make the polynomial equal to 0. Well, if I plug a 1 in for x up here, that makes the polynomial equal to -2, because that's what's in the remainder position. So 1 is not one of my roots. I'll move on and I'll test -1. I'll bring down the 2. -1 times 2 is -2, plus -5 is -7. -1 times -7 is +7, plus 0 is +7. -1 times 7 is -7, plus 1 is -6. Again, if I plug a -1 in for x, that makes the whole equation equal to -6, which is not 0, so I will move on to positive 1/2. Bring down the 2. 1/2 times 2 is 1, plus -5 is -4. 1/2 times -4 is -2, plus 0 is -2. 1/2 times -2 is -1, plus 1 is 0. This is the one that I'm looking for. 1/2 is a root of that equation. That means that the number 1/2, when I plug it in for x, makes the equation equal to 0. So 1/2 is one of my roots. So let's see, if I make a list of my roots up here, I know that 1/2 is one of them. And again, because this is a third degree equation, I know that I'm looking for 3 possible roots. Well, I could rewrite this equation as a product of its factors. So 2x to the third minus 5x squared plus 1. I know that 1/2 is a root, which means that I could actually rewrite it as x minus 1/2. And that will be times this polynomial that is the quotient whenever I used that synthetic division table. So that would give me 2x squared minus 4x minus 2. And that whole thing is going to equal 0. I already know that since x minus 1/2 was a factor of the polynomial, that 1/2 was a root. So now all I need to do is figure out what values of x make this remaining factor equal to 0. You could try factoring it, or if you're not sure if it factors, you could go straight to the quadratic formula. The quadratic formula is x equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. You can always use the quadratic formula when you have a quadratic. We know that in this case, a is 2, b is -4, and c is -2. If I plug those values into the formula, the opposite of b is -4, so the opposite of that is +4, plus or minus the square root of b squared, so -4 squared is 16, minus 4 times a is 2, and c is -2. All over 2 times a, so that's all over 2 times 2. This tells me that x equals 4, plus or minus the square root of -4 times 2 is -8. -8 times -2 is +16. So this actually becomes 16 plus 16, which is the square root of 32. all over 2 times 2, which is 4. Simplifying further, that gives me 4 plus or minus. The square root of 32 is just the square root of 16 times the square root of 2. That simplifies to 4 square roots of 2, all over 4. Finally, I can simplify by dividing each one of these terms by 4, so I get 1 plus or minus the square root of 2. These are my remaining 2 roots. I knew I was looking for 3 total roots. So up here in my list of roots, I already have 1/2 as a root. The other 2 roots are 1 plus or minus the square root of 2. So my 3 roots are 1/2, 1 plus the square root of 2, and 1 minus the square root of 2. Again, I'm asked to find